Hello everybody, this is Avantik here. Today we'll be discussing about support vector machines. The agenda for today's discussion would be introduction to support vector machines, maximal margin classifier, soft margin classifier, support vector machine for classification, understanding the concept of kernels, hyperparameters for SVM, and support vector machines for regression. So let's start with the first topic, which is introduction to support vector machines. Support vector machines, brief introduction here. And before I head start what it is and all that, let's get motivated with the inspirational story of inventor of support vector machines. Vapnik is the guy who invented support vector machine actually way back in 1962. Machine learning community rejected his proposal, saying that there are neural networks which is doing better job, or there are other learning models which is doing better job. So his theory of support vector machine was rejected, and it stayed so for the span of 30 years till early 90s. Vapnik happened to come across some problem that US government was trying to solve, and it was regarding identifying digits and routing postcards. Okay, so the model that was used then was not giving good performance. It was not for failure safe and all. So he proposed support vector machine, and it worked wonders. So it took him 30 years to bring support vector machines to glory. So guys, never give up, keep trying. Okay, with this inspirational story, let's understand what is support vector machines. It is a learning method for both classification and regression, and it can also be used for outlier detection. Support vector machine, unlike your logistic regression or other models, is very well suited for high dimensional data sets. Okay, it uses lesser memory for large amount of data as well. That's because it minimizes the data set which is used in training. Okay, it is also suited for data which has more number of columns than rows with right hyperparameters. With this, let's understand maximal margin classifier, which is like building block of support vector machine. Maximal margin classifier. So this is the foundation on which support vector machine is based on. Okay, let's understand with some example. So we have these red points and these blue points. What we want to do is we want to draw a line in this case which separates this data. Okay, so there are a lot of possibilities. As you can see in the second diagram, we have line this, and many more. So which one to choose? As far as maximal margin classifier, it chooses a line such that it maximizes the separation between these two classes. Okay, and it will consider the nearest points for finding the line. Okay, so in this case, this is the nearest blue point and this is the nearest red point. It tries to predict a line which is at equidistant from these points. So that is what is maximal margin classifier. So as per maximum margin classifier, it is an optimization problem where you're trying to maximize the margin. Margin is the distance between the predicted line and the nearest point. As you can see, this line and this point, this line and this point. Okay, so in case of data which is two-dimensional, it will be a line. In situations where the data, as the dimension increases, it will be hyperplane. Okay, so this is the concept of maximal margin classifier. How it is different from logistic regression, because logistic regression, it uses all the points to find the line. In maximum margin classifier, it will use important points, and later on we'll come to know these are not support vectors. So it considers only this point and this point. Okay, and the fundamental assumption here is there is no overlap. Okay, so no overlap in the data, like there is no blue point which comes here. So it's a little rigid. This is the limitation which we try to overcome, or trying to live with in our next discussion, that is soft margin classifier. Soft margin classifier. Okay, in real world, the assumption with which the maximum margin classifier works does not really exist. There will be always data which is across the boundary, like you see in this data. So you have this line which separates these blue points and green points, and of course there are some data which separates which is which overlaps, right? Like this blue point which is outside this area. So this is what will happen in real situations. Okay, so the idea is to still find the line or a plane which maximize the separation, which is more generalized. Okay, and this behavior is achieved using soft margin classifier. Okay, that means it allows some degree of misclassification. That's how it is different from maximum margin classifier. And based on the C is the trade-off. Okay, with larger value of C, smaller margin will be accepted. That means if you increase the value of C, you allow less misclassification, right? And if you decrease the value of C, you allow more misclassification. Thus, your model is much more generalized. Okay, so this is what soft margin classifier is, and based on this, your support vector machine fundamentally works. Let's now understand what is support vector machines. Support vector machine is similar to soft margin classifier unless the data is not linearly separable. Okay, so if the data is linearly separable, your support vector machine is exactly like soft margin classifier. Now let's get into a situation where the data is not linearly separable. As you can see in this case, you have these blue points and these black points. Okay, and as you can see, you cannot draw a line or a plane which can separate this data. Okay, and let's try to see and do this with code. And how do we transform this data into a representation where you can have a line or a plane which can linearly separate the data. So we are using mixed circles with factor 5, which actually decides how far is this data from each other. Noise is how distribution is the data, and number of samples, total number of data. Okay, and we can see here the data, right? So now what we do is we want to transform this not separable data, not linearly separable data, into linearly separable data, basically to a format where you can draw a line or a plane which can separate the data. To do this, all we can do is, we can have we can derive from this data one more column Z, which is like sum of square of X and Y. They say this is X, this is Y, X square plus Y square, that is your Z, and that is how we calculate NP square. X is 1, so around the horizontal axis it is squaring it up and then it is summing it up. Okay, that is the Z column. So that becomes the height. So if we try to plot a 3D data now, you can see now that's the height, right? You can see this. So now, do you see a line or a plane which can separate this data? Of course, yes. You can see this. A plane which comes from between these yellow and purple points will separate them out. So this transformation is additional thing on top of soft margin classifier. Okay, now this is what SVM can do for you. If you have a data, it can do the transformation such that there is a possible separator now. Okay, this is done by kernels, which is our next concept of discussion. Okay, let's understand kernels now. Okay, kernels are an integral part of SVM. As we discussed earlier, this is what is responsible for transforming your non-linearly separable data to something where there is a possibility of a line or a plane which can separate the data. Okay, so there are different type of transformers or kernels that are available in SVM. Okay, and the purpose of them is basically converting your data to a format such that there is a possible separator between them. Okay, so let's see various types of kernels here. First of them will be linear, then we'll discuss polynomial, then we'll discuss RBF. Okay, so linear kernels is the simplest of the kernel, and what it does is it is simply nothing more than your soft margin classifier. So let's say we have data like this. So we are plotting here columns, last two columns of iris data, and we can see the distribution. And what we want to do now is we want to find a support vector classifier which would actually break this data into 3 classes. Okay, and we want to see the linear separator over here. So SVC is equal to SVC kernel dot linear, telling it that you want it to drive linear kernel first, and once the model is trained, you're using SVC dot fit. Okay, since it's a classification passing the training data versus your target. Okay, and what you see, this is the area, this is the piece of code which is generating all the data between this range. And on plotting it now, you see this is the decision function. Okay, this is the decision line, this is the separator over here. Okay, and for data like this and this, you can see only these 2 points are considered. These are known as support vectors. The red points are known as support vectors. I plotted it this way, support vectors, and you can see there is some overlap in this blue and red. Okay, so little more support vectors are considered, and this is the line in this case. Okay, if you want to see all the support vectors that is used, it is svc dot support vectors. So rest of the points are not considered in creating the decision boundary. Okay, so this is your linear kernel. You're trying to predict a line in case of data which is 2 degree. Of course, if it is higher degree, then you will predict a plane. Okay, let's move to the next kernel, that is your polynomial. In polynomial kernel, what we try to do is we try to predict a polynomial degree line. Okay, say we have data which looks like this, or we are generating simply moon data. Okay, so what will you do? You are creating a support vector classifier with kernel poly. Okay, and I'm generating all the points in that range. And when you plot the decision boundary, it looks like this, a degree 2 polynomial line that it has predicted. Of course, there is some misclassification over here, right? So that's what is your polynomial degree. You're not predicting a straight line anymore. You are predicting a higher degree line. You can configure here. By default, it will be of degree 3. You can configure. When you make poly, you can configure the degree parameter. Okay, this is the degree parameter. By default, it's 3. You can configure higher degrees as well, or lower degrees as well. Okay, so the next kernel is RBF. Okay, RBF is unlike your linear or poly, which is still a line or a linear separator. RBF allows you to be completely nonlinear. Okay, so as you can see, when you configure the kernel as RBF, you get a predictor which is like this. Okay, so RBF can deal with very much non-linearly separable data, so it is very popular for images. So keep it in mind when you are doing image classification or things around images using SVC. Consider RBF. Support vector machines are highly parameterized. Okay, that means you have to configure the right hyperparameters so that it behaves well. Okay, one of the hyperparameters C, the other one is gamma, apart from the other stuffs. Okay, so let's understand C first, and then we'll get with gamma. Okay, C parameter is a trade-off of correct classification versus the generalized function. Lower the value of C, the more generalized the model is, right? It is a degree of misclassification you allow. Okay, so let's see and understand this with an example. So we have a data which is not linearly separable. As you can see, there is certain amount of overlap over here. And when you try to do SVC with kernel RBF and C is equal to 0.1, what you're trying to do is this is the predictor you're doing, and you can see it's relatively generalized. If you increase the value of C, you can see the separator is highly non-linear in nature, right? So you can see it's highly so, and this is why, because with high increasing value of C, it allows lesser and lesser misclassification, and of course now this decision boundary is less generalized. We'll understand the next hyperparameter, which is gamma. Let's understand this gamma. Okay, so fixing C, which is basically allows this decision boundary to be as complex as possible. And with gamma, you are telling how important a point is, right? How important a data is. That's all. So, and this completely gives you nonlinear classification. As you can see, for data like this, it is completely giving this. So, as we understand, a perfect higher value of gamma will make your model with higher variance. Like it might not work the same for testing and training data. So what we have to do is you have to find the right balance between C and gamma. That is where your grid search techniques comes into picture. Okay, so with SVM, it is a common practice to use grid search so that we can find the best hyperparameters. With this, we'll go to the next topic, which is about how do we use SVM for regression. SVM for regression. Okay, let's get to SVM for regression. We have so far seen how SVM can be used for classification. In regression, your target data is continuous. So based on the relationship between the target data and the feature data, your kernel might work out for you. So for example, you have a data like this that you see here. We have generated this data. So for this data, you might have a you might want linear kernel to be used, or polynomial kernel to be used, or RBF. So we want to try for all these things, and based on the relationship, we will find the best fit among them. So that's what we are doing here. Using SVR, we are creating objects of all these three models. We are training the same data for all the models, and we are eventually predicting and plotting the line here, right? So as you can see here, this is the data, blue one. The green one is the linear model. The red one is the polynomial model. The blue one is the RBF model that you see here. Okay, so as we can see, based on the relationship between the feature data and the target data, our model will be chosen and the kernel will be detected. Okay, so if you increase the value of C, you allow misclassification, right? Like in this case, if you increase if there are some points lying far, and if your C is very high, you will you will disallow misclassification. Your relationship line or this plot will be very spiky, right? Whereas if your C value is less, you allow a smoother curve over there, right? So keep relating the different parameters with different different parameters with your variance bias relationship. It will help you understanding the concepts in a better way. Okay, thank you guys.